Hello everyone, my name is Sebastian, and I'm one of the co-founders of DC Spark as well as Pima Studios. And in this video, we're going to be talking about Cardano 2.0, which is this new version of Cardano being developed that mostly takes the form of two very important upgrades to the core consensus. One is Leios, which will massively improve the throughput of the Layer 1 blockchain, as well as Peras, which will improve the finality of the blockchain as well. So with these two together, you'll be able to have a much more scalable blockchain with finality being much faster. So websites and dApps and tools can react to Cardano blockchain events much faster. All this without sacrificing decentralization. So it'll be a really important update to Cardano. Now, this 2.0 moniker is not just the combination of Leios and Peras. It also encodes the fact that Leios is actually a lot more complex than Peras. Of course, they're both complex systems, but Leios requires quite a lot of rethinking about how the core consensus code base works. And so if we're making a very large update to Cardano itself to introduce this new protocol to massively improve scalability of the system, should we take this as an opportunity to change more things about the protocol as well as we do this kind of consensus code base rewrite? So this video is mostly for people who are interested in kind of the weeds of things. And so, as you might know, Cardano has decentralized governance, which means people in the community will have to vote at the end of the day whether or not they want to pursue these changes and how they want to pursue them and how they want things to be implemented. And so it's important that people in the community understand these details and the trade-offs of these different approaches. That way they can have a vocal opinion online, and the community can together decide what the best decision is. And so that's kind of the purpose of this video. And so we'll go over what Cardano is thinking about, notably what IOG is thinking about, as well as what some other blockchains have done and some other people in the industry are looking at in different projects. So you have a more holistic idea of the industry and how Cardano is trying to think of this rewrite. And so that's kind of the background on this video. So just some quick history first. Cardano's has had already two versions. So in 2016, there was Cardano SL, which was the first version of Cardano that ended up becoming the version on mainnet. So that was the Byron era of Cardano, the very first version that launched on mainnet. Later on, the node was rewritten in 2019, which is called Cardano Node. And this version was meant to be to move over from like the proof of concept version of Cardano to something that follows a lot more formal methods, has better specifications, and all these kinds of great things people have come to learn and love about Cardano, including, of course, Shelley, which introduced the proof of stake protocol. So that was the kind of history. And so you can see from these dates, 2019 is already 5 years away. And so if we're thinking about making some big changes for Leios, technical debt does kind of accumulate over a 5-year period. And so it also kind of makes sense within this context to think about, sorry, my head's kind of blocking it, to think about if we're to change some of the things, take some lessons learned, what should be done better? So within this, one of the main things that comes to mind is the API of interacting with Cardano. That's to say, of course, Cardano has a lot of things that it does, the consensus side and in the smart contract side and all these things. But how do you actually get data out of the node? So you're running a node, you're running a Cardano node, and it exposes API, and people interact with that API from dApps, explorers, and so on, right? And so this API kind of plays the role of connecting the node to the outside world. Now, notably, Cardano has a very, very limited API, and this was done on purpose to try and keep the node as simple as possible. If the API of the node is very complex, it makes changes harder to do. It puts more CPU requirements, more memory requirements, more storage requirements on the node, which increases complexity. And a lot of the goal of Cardano is to build something that's really decentralized, which means you want to have the lowest CPU requirements, the lowest memory requirements, the lowest storage requirements, so people can run nodes all over the world. And so this choice to have a relatively small API was made with this decision in mind. However, you can see how this decision impacts downstream apps and explorers. So for example, in Ethereum world, you have endpoints like ETH get logs, which gives you events emitted by a smart contract, and you have stuff like ETH get balance, which gets you the balance of an account. And so just by running a node and no other external tool, you can already get a lot of the functionality you need for a basic application. Which is like, okay, you want to build a dApp, well, what do you need? You need to be able to get events from your smart contract. You need to show the user their wallet and their balance. And with just those two things, you often get like a lot of what you want. And so a lot of this stuff kind of comes built in out of the box. Cardano rather implements something called mini protocols, which are not things you can easily query from the dApp side, and usually they require wrappers. So from the Cardano side, you've probably seen a lot of these tools out there, like Aura, like Carp, like Scrolls, like DBSync, like Ogmios, and so on. And so there's a wide variety of tools out there, and this makes it a bit harder to spin up your infrastructure. Now, there are definitely startups that handle this. Like Demeter by TXPipe, as well as Blockfrost, which is now by IOG. And so these are kind of the equivalents of tools you might see on the Ethereum side, like Infura or OpenNode, and so on. So Cardano has these kind of RPC providers so that people don't have to run their own infrastructure. They have like an opinionated API. But there's a difference between how Infura works and how these tools like Demeter and Blockfrost work in the Cardano world, which is that Infura, although they do have their own custom SDKs, and Alchemy has their own custom SDKs, and they all have custom stuff, the main service they provide is exposing these API endpoints that exist as part of the core node in Ethereum. They of course have their own custom stuff to make their services usable for specific use cases, but a lot of their service relies on leveraging the APIs already built in the node. Whereas some of these other tools on the Cardano side, Blockfrost, Demeter, and so on, they do not re-expose an API on the Cardano node. Rather, they wrap the Cardano node API with some of these other services and expose those to developers. Now, this gives you a much larger flexibility in the sense that in EVM land, if you don't have the API you need from the node, too bad, you're going to have to try and make it work. But on the Cardano land, because you have a lot of options, there's a lot more opinion APIs, but it does introduce fragmentation, right? There's no standard API that everybody uses. You end up with a lot of different infrastructures, a lot of different standards, and this makes it hard to kind of unify around a certain interface, which can hurt interoperability from a tooling perspective. And so there's obviously advantages and disadvantages of every approach. And so although in the EVM land, there's of course RPC providers like Infra, there's also custom indexers. So there's not just like the ETH get logs stuff. There's also like customs indexers like the graph. So there are companies building like custom stuff. People are mostly using these logs, which is great for interoperability, but bad for flexibility. And on the Cardano side, you get a lot of flexibility, but it makes it harder to reuse infrastructure across different projects. And so this question of should this be done differently? Should we expose more information as part of the node to make this lesser problem, to enable having more flexibility and more interoperability between different tooling out there without overly increasing the burden on the node itself? And so we'll kind of go down in this video how EVM is handling this, because obviously they have the same problem from the other side, which is, okay, how do we make upgrades to our new consensus that's coming out in a way that makes sense? And then Cardano has the opposite problem, which is that they want to potentially expose more stuff. And so we'll see the difference between these two in this video. Move down. Well, that's not supposed to happen. There you go. All right. Great. So first, before we go deeper into EVM and Cardano, let's maybe talk about roughly the approach of how you would solve this problem. So you want to have a node, and you want to keep it small, but you want to be able to connect the node to some other systems that can introduce additional functionality. You want to make this kind of a first-party system, so you can increase the functionality of the node optionally, and then you would take all of this and then expose this as the API. Right, this is essentially what we want to do. That way, if you want to run a node that is still very slim, has a low CPU requirement, low RAM, low storage, you can do that. But if you want to extend your node with more functionality to be able to provide these indexer services or these APIs, you have that choice. So conceptually, this is what we want to achieve. Now, how do we actually achieve this in practice? There's essentially two main approaches that you see in the industry. So one of them is having a common compilation target. What does that actually mean? That's a bit technical. In computer science, there's actually different steps to having a computer program run. So oftentimes, people will write their program in a programming language. So this could be Haskell, could be Rust, could be JavaScript. And although not in all cases, oftentimes these programming languages oftentimes these programming languages, not always, but oftentimes they end up having an intermediate step, and then down at the bottom they run on your CPU. So there's some intermediate step, and then they run. Now this intermediate step nowadays often ends up being WASM or RISC-V. Now, of course, in practice, there's often like many steps. There's not usually just one. But for simplicity, we're going to look at this part of the stack. So the key thing is that a lot of these different programming languages do have ways to compile them into either WASM or RISC-V. And so when I say common compilation target, I'm mostly talking about interoperability by having different programming languages be usable as long as they all compile to the same compilation target. So a great example of this is Polkadot. So Polkadot is based on a framework they've written called Substrate. So Substrate is a SDK for building chains, and so Polkadot is based off their Substrate SDK. But different other chains are also based on this SDK. So for example, you might have heard of Midnight, which is this ZK project built on Substrate. You might have heard of Avail, which is a DA layer built on Substrate. You might have heard of other blockchains for a large variety of use cases, bridges, real-world assets, games, and so on, also being built with Substrate. So there's a large number of chains built with substrates. And the Substrate SDK works through a system called palettes. That's maybe too close to me, so maybe you won't be able to see that. works off a system called pallets. And essentially what this pallet system allows you to do is have a lot of built-in functionality that you can leverage and don't have to write yourself, and you can combine these together to build your chain. So for example, if you want consensus, so Ouroboros like consensus in your blockchain, they have a system called Babe, which is based off of Ouroboros that you can add. And if you want RPC endpoints to get balances, they have a pallet underscore balances you can enable. If you want like a governance palette, they have a palette for that. And if you want proof of stake, they have a palette for that. And so they have a lot of different palettes that you can take and use them together to build your own chain blockchain, like Midnight, like a Veil. And these palettes, the way they work is through a system called Frame, which is like their core system that manages all these palettes you've picked together. And the way it manages composing these different palettes into one executable is by having them all compiled to WASM. So this is great because it means that people can extend the core functionality of the system by just writing a custom palette. And as long as your custom palette compiles to WASM, usually it's written in Rust, but it doesn't have to be in Rust. As long as your system compiles to WASM, you can compose this together with these other palettes. So it allows you to have, if you want, like a really slim node, but you can add more functionality to it if required. Now the Polkadot side, they're more focused on Substrate, which is trying to build custom chains as opposed to extending Polkadot itself. But you can kind of see how the concept applies, which is that you can have a base system and you can have these palettes, as long as they all use WASM, can be combined together. And we'll see another example of this that Ethereum's thinking about briefly. But before we get there, we'll go into approach number 2 that people are thinking about, which is message passing. So what is message passing? What's the difference between message passing and these kinds of common compilation target strategies? So with message passing, instead of having one base where you combine them all together into one binary at the end of the day, you instead have multiple applications that pass messages between each other. And these are often separate processes. So completely different programs in your computer that pass messages to each other. And oftentimes there's kind of a coordinator in between that handles passing and receiving messages and forwarding messages along to whoever needs it. And so an example of a chain that uses this model is Cosmos. So Cosmos has the Cosmos SDK that again is mostly geared towards allowing you to build custom blockchains, and their system works primarily on message passing. So again, anybody can write their own, EVM compatible Cosmos SDK system. They have, Tendermint, I believe, which is like their consensus system that you can download, and they have a whole bunch of other systems you can set together. And basically, you choose which components you want, and then they all get coordinated between each other through this message passing system. And so this still gives you the kind of system that you want to have, in the sense that you have a small node, and the node's goal is primarily just to facilitate this message passing between different protocols. And so if you want to run just like a slim node, you can have just like your slim node. But if you want to have these messages get passed to a more complex system that introduces new custom handling, you have the option to do that. And so the important thing to note is that there's a much smaller amount of cohesion between these things. So instead of having everything compiled to one target and you group everything together, right? These are separate applications, separate systems, and you're just passing messages to each other. And so it's much more loosely coupled. So these are the kind of two approaches, and because the because the message passing system is more loosely coupled, there's no requirement for common compilation target. This is say you don't have to say, okay, all these have to be WASM. You don't have to say all these have to be RISC-V. You can have one be Haskell and have one be Rust and have one be JavaScript and have one be something else. And there's no kind of limitation as long as they understand the message format between processes. This is sufficient. And so this gives you a bit more flexibility in how these messages and components talk to each other compared to the common compilation target approach. So now that you have some background on two of the main systems out there for building blockchains, which is Substrate and Cosmos, there's of course other ones, but these are like the two main market leaders on as far as like SDKs for building custom chains. Now let's look into Ethereum and Cardano and what they're thinking about to try and solve their problems of extensibility without bogging down the node. So let's talk about Ethereum first, because I think Ethereum is already pitching a specific vision to the community at DevCon, which is going on right now, the time I'm recording this video. And so you can find videos online of them talking about what they're doing. So if you look up keynote title redacted, you'll see the presentation by Justin Drake from the Ethereum Foundation at DevCon talking about their approach. But Vitalik Buterin, which is the founder of Ethereum, one of the founders of Ethereum, also has a series of blog posts on his roadmap talking about what Ethereum is doing. And so since this one's a bit more concrete, it gives us a good way to compare against them. And then we can talk about Cardano, which is a bit more at the early stages of deciding which approach to go with. And I caveat this by saying Peras and Leios are not at the early stages. These are like very well understood research problems with papers and blog posts and everything. I'm purely talking about separate from the implementation of the research papers, which is what do we do about Cardano itself? Do we want to rewrite it? Do we want to keep it the same? If we do rewrite it, how do we rewrite it, right? So this is still like an earlier discussion, and so this video is meant to kind of share that with the community. So with that, let's kind of look at Ethereum side of things and what they're thinking about. So note that in Ethereum, the main client out there is called Geth, which is Go Ethereum. Go being a programming language. Fun fact also, although Substrate is mostly Rust, Cosmos is mostly Go. So this is a very commonly used programming language in the blockchain space as well. So Ethereum, there's many clients out there, but Geth is the largest one. And Geth introduces, not just the implementation of the Ethereum virtual machine, which of course is used by not just Ethereum, but also the different EVM forks out there, as well as all the layer 2s out there. It also has this concept of precompiles. So precompiles are a way to extend Solidity smart contracts with new functionality that is not part of the core EVM programming language. And this is often used to introduce functionality that is not easy to write as a Solidity smart contract. So it's often used for cryptographic hash functions, but also sometimes used for very app-specific chains. So for example, you often hear about like a startup that has a specific use case in mind, for example, gaming or real-world assets, and to accomplish this use case, they need a specific functionality to be very fast and just built in that every dApp can use, and so usually they use precompiles for this. It's a way to extend the core of the Ethereum implementation with new functionality. The problem with these precompiles is there's two main limitations. One, it requires a fork. Right, you need to run your own custom EVM chain which is why you hear a lot, on Twitter and so on that, projects, XYZ, just announced that they're launching their own EVM fork. Oftentimes that's motivated by precompiles. They want to have a custom precompile, have one custom flexibility, and unfortunately, having that requires them to fork the chain to have the precompiles they need. 2 is they need to be stateless, which is more of a technical restriction, but will be related to some discussions later on. That's to say they can't keep internal state. So you can't easily write a precompile that's like a proof of stake precompile that keeps track of everybody's staking balance on the entire chain, because this requires keeping track of this state of which account has how much balance. And so the stateless limitation avoids these forks being able to write some of the precompiles they want, which is why you sometimes see projects like Evmos and so on that try and build new custom clients for Ethereum that are not Geth based entirely, that try and add like stateful precompiles. And so another one that we'll talk about is Reth, which is Rest Ethereum, which is a competitor client to Geth that's trying to add precompiles. And it's not entirely related to stateless systems versus stateful precompiles, but it's related to trying to build competitors to Geth that are more flexible, right? So why is there an interest suddenly in building new clients that kind of replace Geth with more functionality? The reason why is because if you look at the Ethereum roadmap for what some people are calling like ETH 3.0 or Beacon Chain, or not Beacon Chain, Beam Chain, a lot of it revolves around actually you're removing functionality from the main node. So they want to remove stuff from the core node. So that involves, potentially less opcodes as part of the EVM. It involves, potentially less precompiles built into the Ethereum itself. And involves wanting to just in general make things much simpler. And the way they want to achieve this kind of reduction in functionality is in 2 ways. One, rewrite as solidity. So as many things as possible, remove them from the core protocol itself and just move them to being a smart contract. And 2 is leveraging zero-knowledge cryptography. So this might seem a bit weird that they might want to remove functionality and potentially rewrite it as a slitty, which is slower, or leverage ZK, which is harder. But if you think about the way that Ethereum is designed, it's always been designed with trying to do as few things as possible in mind, which is similar to Bitcoin, similar to Cardano, similar to any protocol that tries to maximize decentralization. And so the way that Ethereum has achieved this is by as much as possible not enshrining things into the core protocol, not adding things to the core protocol. This is a proof of stake in Ethereum is a smart contract, tokens in Ethereum is a smart contract, governance is Ethereum, smart contracts, DEXs, smart contracts. Like as much as possible, everything they do, they just make them smart contracts and try as much as possible to avoid adding them to the core protocol. The problem with this approach is that it often leads to dangerous or hard to understand user experiences. And so, for example, because in Ethereum, tokens are just smart contracts, there's a lot of complexity around handling tokens. There's a lot of ways for users to accidentally lose their money using tokens. It makes wallets harder because when you're using a tool like MetaMask or a Phantom or some of these other EVM-compatible wallets, the wallets often have a harder time showing you what the transaction will actually do. Like, will it sign this transaction, do what the dApp says, or will it just drain your entire wallet? It's hard for dApps to know because these are not protocol features, stuff like tokens, are just smart contracts. And so a lot of the ways people have tried to compete with Ethereum from a layer 1 perspective, if you're building a layer 1, the main way to compete with Ethereum has always been to enshrine as many things as possible into your protocol. So you can say, well, our new blockchain is much easier to use than Ethereum, much easier to develop on than Ethereum, much safer to use than Ethereum. And so people tend to enshrine things in the layer 1. That's why you see a lot of blockchains nowadays have token standards enshrined as part of the blockchain itself. So I see blockchains have proof of stake enshrined as the protocol itself, governance enshrined as part of the protocol itself. It's not just because there's definitely advantages to enshrining, but also because it provides as an alternative to what Ethereum has done, which is trying to make everything smart contracts. And so the enshrining gives you a lot of benefits. The downside is that it's logging in certain design decisions. So one of the benefits of this looser approach of Ethereum is that if you don't like the token standard and you think things should have been done differently, you can write your own token standard. And so stuff like NFTs and semi-fungible tokens and all these kinds of various token standards that have come out are enabled by the fact that tokens are not built in layer 1. So it empowers people to experiment a lot more than they would be able to otherwise. So following that philosophy, they want to kind of keep pushing on that direction and try and remove some stuff from the protocol. Notably, a lot of the technology that has enabled them to try and push this direction is zero-knowledge cryptography. So if you don't know, zero-knowledge cryptography is a technique that allows you to have mathematical proofs of the correct execution of something. So that's to say, before zero-knowledge cryptography, you used to have a computer program that was a bunch of lines of code. And this would, for example, be your precompile. And how do we know that the precompile is correct? Well, every time somebody uses that precompile, so you have some, solidity code. Every time somebody calls that precompile, what it does is it goes into it. Runs the entire execution, and then returns. And so because the precompile execution is part, in a sense, of the execution of your smart contract, and the smart contract is run by every node, and the network is secured by Ethereum's proof of stake protocol, everybody can understand that the precompile was executed correctly. So Ethereum operates by having every person rerun every smart contract, right? Which is the same as most systems out there. But you can see how this leads to a scalability issue, which is that if every single person running Ethereum node all has to rerun every program on their machine, this is redundant, right? Of course, this was historically required for safety, because if you trust one person to execute it on your behalf, then you lose security. But ZK came in to kind of revolutionize this model. So in the ZK side of things, instead of running the entire precompile and then returning, what instead you do is you have you could call this like a ZK precompile, but it could be like some kind of ZK application. What you do is still you call into the ZK precompile, you still do the computation, but at the end, you instead of just ending there, you generate a proof of the correct execution. And so this proof is done in a way that does not need to know what the actual precompiled code is necessarily. In the sense that from an Ethereum client point of view, precompiles are built into the actual code base. Like they're actually parts of the node. Whereas in this version, what you have is just instead of generic ZK proof verify, you just have a generic ZK proof verify precompile in a sense. And it can support any kind of arbitrary precompile system. So it means that instead of having, maybe like 50 precompiles inside the blockchain, you could maybe just have like one precompile that's just a one ZK verified precompile. And through that, it allows anybody to create their own systems. And Ethereum doesn't have to know about how all these customs systems work. All it has to do is know that any different system written by anybody else can all be verified using the same ZK proof verified precompile. Right? And so the fact that zero knowledge cryptography has advanced so much is what is motivating Ethereum to try and reduce the scope of the programming language from an EVM perspective and reduce the number of precompiles and move more towards what you see with ZK VMs. So you might have heard of ZK VMs. And when I say ZK VM, I do not mean ZK EVM. Let me kind of describe this. So note ZK EVMs are not the same as ZK VMs. ZK VM is more a general term. ZK EVM is a specific term, which is a ZK VM for the EVM specifically. So it's like within all the ZK, all ZK EVMs are ZK VMs. Not every ZK VM is ZK EVM, right? So it's like a specific version of it. So ZK VMs are zero knowledge based virtual machines, where instead of having general smart contract programming languages like Solidity does, they instead just have ZK proofs as the core concept. So some of these you might know is Midnight. You might also know Mina. There's other ones coming out like a Leo. There's different ones that work on different proof systems. So like Starknet, Nexus, Nova. There's too many to list, but like there's a bunch of new blockchains coming out. They're trying to tackle this kind of ZK VM concept, where instead of having every node run every proof, rather you just have a verification of these computations. And so this is one of the main reasons why Ethereum is looking into simplifying the core protocol, because they're hoping that ZK VMs are very close to being basically just as good as non-ZK stuff. And so given a few years, it'll just keep getting faster. And so maybe it makes sense to simplify the Ethereum system and move as much as possible to leveraging ZK. But if you're removing stuff from the system as much as you can, how do you, and to kind of tie it back together, what do you do about the API? Right, so remember we talked about how people want to add custom systems, they want to use the ETH get logs and ETH balances, and these other endpoints. And maybe we can introduce a kind of more complex example of some way that somebody might want to extend the system, so you can get a good idea of not only how they're trying to maintain API compatibility, but how they're trying to extend the APIs that people can create while not breaking compatibility with the ZK vision, right? They want to enable people to extend the API, but not do this in a way that breaks their ZK roadmap, right? So to see an example of this that's getting a lot of traction right now is we'll look at a concept called shadow logs. So first, before we understand shadow logs, we have to understand what is logging in Ethereum. So if you have a Solidity smart contract, you, for example, have like a function, maybe I'll give it a more real name for this example. So maybe you have a function inside your smart contract called transfer. right? When this function gets called, it has like an address of who to send funds to. And then within this, you have some actual code to do the transfer. But then they'll have a kind of emit keyword that says like emit transfer, maybe like transfer complete address. So I know this is a bit like codey, so if you're not a programmer, this might seem a bit uh, hard to understand. But the key thing you need to understand is that whenever you're calling into the smart contract, it can trigger an emit, which sends an event, and anybody can query these events using eth get logs. So it means that if you want to write a website, a dApp for your smart contract, all you have to do, you don't have to run any custom indexer, you don't have to write any custom system. All you need is the eth get logs endpoint that's built into the node itself. And you say, okay, I want to get the logs for transfer event. And then usually you also specify like the contract address. So you say, like, okay, my contract, this is maybe deployed at like 0x43, blah, blah, blah. And then 43, blah, blah. So note that there's no need to spin up a custom indexer. There's no need to write any custom system. You can just call eth get logs, specify the event that was emitted inside your slave smart contract, and then this will give you directly access to your smart contract event from JavaScript or these other systems. So this is really great because it means that as a developer, I don't have to spend a lot of development time and a lot of development effort connecting to my smart contract from my website, from my backend, and so on. I just need to use eth get logs, and that's basically it. The problem with eth get logs is that it has an actual cost to it. You can see that this whole emit and transfer system is actually part of your smart contract. So it's actually in Solidity, which means that there's a gas cost involved in not just adding your smart contract to Solidity, but there's an actual gas cost on the emit. Every time emit gets called, it increases the gas cost of the transaction. So it means that you're adding this eth get log system just for you as a developer to easily be able to write your JavaScript smart contract, or the JavaScript part of your smart contract, and so on. And despite the fact that you're only doing this for development purposes, you're actually incurring a gas cost on the users of your blockchain, right? And so this is not ideal. The reason it's not ideal is if you look at a complex system, like for example, Uniswap, right? It's a large project with a lot of different stuff going on. They have, dashboards to try and understand how their smart contracts are doing, how many users they have, how much liquidity they have, what are people doing, right? Uniswap has a lot of analytics. And the easiest way for them to build their analytics is to use these events, right? It's built into Solidity. There's a lot of good tooling for it. They want to use these events. But they can't add as many events as they want because the more events they add, the more gas cost they incur on their users. So they might actually, like the gas cost of all these events in Uniswap is over $1 million across all the users across the entire history of Ethereum. So there's actually like a non-trivial cost you're incurring onto the users just to add more events. So the benefit of having these events part of the slave smart contract is gives great interoperability, right? Uniswap can write a front end, somebody else can write a front end, somebody else can connect the system, right? I don't have to be part of the Uniswap team to have, my own front end. I write my own website, and my website also reads in the events because they're all coming from the blockchain itself. So these event systems are not only great for improving the developer experience, they're also great for interoperability because it means that any company that wants to leverage the Uniswap data does not need to go figure out Uniswap's proprietary technology and figure out how that works. They can just look at the Ethereum smart contract, look at these events, and pull these events themselves. So the interoperability of eth get logs is really awesome. But there's also a real problem, which is that they might want to log more, but aren't able to. And so through this concept, there's this idea of shadow logs. So now that we know what logs are, what are shadow logs? So we still have our Slate smart contract. We still have our Slate smart contract like before. We still have our transfer event like before. But now we have the option to kind of like shadow log our event. And the important difference is that when your smart contract gets compiled, this part is actually removed. So actually on chain, this shadow log never appears. So you incur 0 smart contract cost for adding these logs. However, if somebody has their like modified smart contract with these shadow logs, you can rerun the computation yourself locally and get these extra events. So maybe to explain it a different way, it used to be that you had a very simple compilation path, which is you have your Slate smart contract, you compile it, you get EVM, EVM code, and then that's what gets run on chain. In this new paradigm, there's now 2 outputs. You compile your Slate smart contracts, and you get still the EVM like before, where these shadow logs are removed, these no longer exist. And then you get some kind of like new like EVM plus, which is like the core compilation plus these extra shadow logs that are not actually stored on chain, but are this new extra thing that if people run this kind of modified version of the system, they can run and get these events. So great, now we have this concept of shadow logs, which is super useful. But wouldn't it be great if we can leverage the entire Ethereum infrastructure for the system, right? We don't want shadow logs to be this, go download this proprietary SDK and call this proprietary system, and don't use this tool, you have to use this custom tool, right? Then you lose the entire network effect of the infrastructure, which is really bad. And so people want to be able to extend the API of Ethereum while still leveraging the network effects of Ethereum. And so the way that some people are thinking about this is with Reth, which is like Rest Ethereum, which is a new upcoming client primarily funded by Paradigm, which is a venture capital firm. And they have a custom system called EX, which is execution extensions. And these execution extensions allow you to install custom extensions into your node that then gets included as part of the node binary. So you have your RESTful node. And again, the goal is to keep this Rust node small, with small memory footprint, small CPU, small storage. But then people can write their own plugins for it and then connect their plugins to it. And this works as long as all the plugins have the same compilation target. So this is like a compilation target approach, if I remember correctly. I know they have an event system like notifications, but if I remember correctly, it does require you to have the same compilation target at the end of the day. But it does use like some message passing stuff within the same process. So it's not like the inter-process message passing you see in Cosmos. So now you have this execution extension, which allows you to have this kind of small node with plugins to extend the API. So you can have, these shadow logs as part of a plugin. So just by running the Rust node, you can get the default behavior. So if you want to run a Ethereum full node locally at your house, you can run the base system. But if a company wants to run a more powerful node with extra functionality for their specific dApp, they can now run this kind of like shadow log enabled version of the Ethereum node. So it allows you to still have like a core simple node while still allowing you to extend the API as needed through this system. And so as Ethereum is trying to simplify their protocol and move stuff more and more towards ZK, this kind of option like what Reth is providing, where you can build these execution extensions, becomes increasingly important. And notably, one of the key things is that right now there's a lot of ZK VMs coming out, like I mentioned, and one kind of ZK system that's really gaining traction are general provers. So a lot of the ZK systems I mentioned earlier, so for example, like Midnight and so on, they require you to write custom smart contracts in like a custom programming language. Sorry, this is, maybe I should use different colors for these. Let me. Switch colors quickly. So a lot of these historical ZK systems require you to write in a custom programming language. So for Midnight, for example, you have Compact for the programming language, and the VM is Impact VM, and so on. So they have their own custom ways of writing smart contracts. These general provers use just WASM or RISC-V. And so the benefit of these systems is that you don't have to rewrite any code. It works as is, as long as your program uses one of these common compilation targets. Now, the reason these general provers are so important, and just by the way, so you have some names, you can look into SP1, Jolt, Nova. So I think Jolt and SP1, I think they're both RISC-V, if I remember correctly. Nova is WASM. There's some other ones out there. So the important thing about these general provers is that because they don't require you to change any part of your code, you can run them on the Rust node itself. So you don't need to write custom ZK Ethereum from scratch, writing custom programming language systems for your entire blockchain. You can take your existing non-ZK, like traditional programming language programs like your Rust node, and then just run them through these general provers. Notably, SP1 is the one getting the most traction for this right now. And the performance of this is actually not that bad. Now you're gonna be kind of scared about these numbers, so it's not like perfect. But right now, if you want to prove like a 12 million gas block using, I believe, SP1, but I don't remember which ZK system these benchmarks come from, it takes about 20 minutes to generate a ZK proof of the block. So 20 minutes of computer time is not for free, because you have to have a computer and you have to pay the gas, or not the gas, the electricity cost. But this ends up usually being like less than $1 per block. So dollar cost wise, as long as you have like access to cheap servers and cheap electricity, this is actually not that bad. And if you look at the ZK technology, this gets better every year. So, maybe it's 20 minutes now, but maybe in a few months it's 10 minutes. And then maybe next year it's 5 minutes. And it just keeps going down. And so what a lot of teams are trying to work towards is, quote unquote, real-time proving. And so trying to get this down to just being like, 10 seconds, because if it's 10 seconds and the block time for Ethereum is 12 seconds, then you can generate the proof faster than blocks get made. And so you can have real-time proving, which is why Ethereum is so interested in this kind of ZK-ification of their platform. That's why their roadmap is not like a 6-month thing. It's like a year thing, because it's not just engineering work that needs to be done on Ethereum. It's also the fact that you need to wait for these proof systems to get faster. And so with these general provers, you can combine them with these nodes like ref. And the important thing to note is because these execution extensions get installed in the Rust node itself, it means when you run these general provers, you're not just getting a proof of the Rust node, you're also including your proof is these execution extensions as well. And so this means that you can use these kind of execution extensions to build not just stuff like shadow logs, but also build like custom layer 2s or rollups with a system like Reth, where you get not just a proof of like the chain, but you get a proof of like your custom precompiled you wanted, or any like other custom system you wanted. So it allows you to get this kind of like Polkadot like experience, but where we have everything like ZK provable in a sense. So hopefully this gives you a good idea of message passing and compilation targets and how all these kind of techniques come together, especially in the context of ZK, which is this very fast growing field. And so when it comes down to it, the question is, for Cardano 2.0 is, do we rewrite, right? So should we keep the old code base or create a new code base? And if we do a rewrite, do we want to change how the API is structured, right? Or do you want to keep with the mini protocols which we had before? And if the answer is yes, do we want to do this through message passing, which is this much looser system where people can write their own components, their own programming language. So you've heard Charles talk about like a polyglot node. So you have different teams working in different programming languages. You have a very loose group, which makes it much easier to coordinate because people don't have to use the same system. They can be much more loosely coordinated. So you want to use this message passing system. Or do you want to use this kind of like common compilation target system, which requires like a more rigid infrastructure and is no longer accessible to every programming language, because now you can only use systems that compile to, for example, ROS, and if you just decide to go that option, or has to compile to RISC-V if you decide to go that option. So there's more restrictions, but it is easier to compose with the ZK systems, because otherwise you still can do like the ZKification with message passing, but what's required is that every component needs to independently be ZK verifiable, and it needs to be independently ZK verifiable with the same proof system, because then you want to have a, for example, like maybe I can draw this out so you get an idea. You have your component 1, component 2, component 3, and there's like some kind of coordinator, and the coordinator sends messages and maybe gets like some responses back. So it used to be you send a message, maybe change colors, and you get a response, right? That's like the traditional message passing system. But you can do is instead you do message response plus it proved that the message really did get emitted. The proof that there really was like maybe the message comes from here. This proof contains that this component here really did send a message, and the message really did come through and came all the way here. So their proof encodes this, and this component runs some code and then generates a response with a proof of the response. And so you can achieve this with techniques like recursive snarks and folding schemes, which is like a different technique but same concept, which allows you to like combine proofs together so that this doesn't blow up out of control. And so this is definitely possible, but it's more complex. And so, fortunately, IOG is doing research on this in the sense that Midnight is a recursive snark based blockchain. So IOG is very familiar with this domain. Us at Pyma Studios, we also do a lot of work with recursive snarks. We've been working with them for years. We've also started doing work on folding schemes as well. So this approach is more complicated to get everything working. Typically does not work with these general provers, but there is a path to go with this approach, but still make it ZK compatible. It's just more engineering work together. And so there's a question of which of these two approaches do we want to take, and this is what IOG will probably end up pitching. They'll pick one of these two that they feel the most confident about, and they'll pitch this to the community. But you might see other projects potentially pitching other nodes with different directions, or you might see people saying like, I want to support the IOG decision, but I think like on top of Leios and Peras, they should also implement not the message passing, but the common compilation target. So you'll see kind of some of these debates come up, and you as a potential Cardano holder or somebody who already owns ADA will essentially, because you're part of the governance system, have a say in which one of these systems gets decided. And so this is the excited part of decentralized governance, where you have to understand at least some amount of these technical decisions to make an educated vote. Cardano does have a DREP system, which is that you can delegate your ADA to somebody else. If you're not confident enough to make a technical decision yourself, you can delegate your ADA to a DREP. Oh, sorry, this arrow should go the other way. And then your DREP will vote on your behalf. So you might be a developer, you're very confident about your understanding of technologies, you might want to vote yourself. But if you're not familiar, you can delegate your voting power to a DREP who potentially is somebody who's deep in the technology, and they will vote on your behalf. Note that in the DREP system Cardano, there's no risk to it from a financial point of view. That's to say, you're not giving your ADA to anybody, you're delegating your vote to somebody. There's no financial reward for doing this, so there's no like incentive for doing this. So you don't have to do it. But the DREP system does have this system in place where if you do not delegate to another DREP or self-register, you will stop being able to withdraw your staking rewards. So if you haven't already, you should either register as a DREP yourself, or delegate to a DREP, or choose one like the always abstain or some of these other options. So you got a few choices. I'm not going to go into the whole DREP system in this video because it's already long enough. The reason I bring this up is because I am also a DREP. So if you watch this entire video and you're still not sure what to do, you can always delegate your voting power to me. And I've been working Cardano for many years, so I'm very familiar with all these decisions, and happy to listen to your feedback and try and make decisions that are best for the protocol. So with that, hopefully that kind of gives you some good insight into Cardano 2.0. And if you have any questions, definitely hit me up online.